Hello everyone, welcome back to my YouTube channel Explore Physics. So previously I have uploaded a video on quantum mechanics wherein I have given a lecture on origin of quantum mechanics. Now in this lecture, which is the second lecture, in this lecture I will be covering black body radiation. So to begin with, first of all let's say what is a black body. So basically a black body is something which is a complete absorber or a complete emitter. So perfect absorber of all radiation. So black body is something which is a perfect absorber, or you can even call it as an emitter of all sort of radiation. So whatever radiation you make it pass through a black body, it will absorb the radiation. So that is known as a perfect idealized black body. Alright, now if you want to give an example, a perfect example of a black body is a black hole. Alright. Why do we call black hole as a black body? Because in this black hole, whatever particle or whatever radiation passes through this, it will not escape, it will fall into this black hole. So that's why black hole is a perfect black body example. Okay, so after performing some experiment and with the data, they have plotted a graph between energy density u nu in the y-axis and frequency in the x-axis. So from the data from various experiments, by absorbing very different data, what did they find is they find an experimental curve for a black body, which is approximately like this. So sorry, not like this, something like this. So it will start from 0 and goes to a maximum and then comes back to minimum. So this is the curve that they have observed experimentally. Okay. Now to explain this particular curve, some concepts from electrodynamics and thermodynamics has been used by scientists, and they have arrived on an expression known as energy density. So energy density expression was given by Jeans number into average energy per degree of freedom. Now this Jeans number can be written as 8 pi nu square by C cube into average energy. Now this average energy can be found by this formula. E bar is equal to 0 to infinity E exponential minus E by kt divided by exponential E power minus E by kt. So by solving this, you will get a value equal to kt. So that is here. So instead of E bar, you will get kt, which is the average energy per degree of freedom. So this is the u nu expression. By taking concepts from electrodynamics as well as thermodynamics, they have arrived at this expression. Okay, so just remember this value. So this was actually explained by classical. All right, just remember this expression. So your expression was u nu is equal to 8 pi nu square by C cube into kt. So this was your expression, right? Now just consider two cases. Case number 1 for lower frequency, that is nu tending to 0, that is lower frequency, right? So just apply that limit in this particular equation. This is your main equation number 1. So in this equation you are applying two different cases. One is for lower frequency, another one is for higher frequency. So the first one is lower frequency. Lower frequency means nu is tending to 0, the lowest value of frequency. When you are applying it in u nu, which is your energy density, you will be getting, so when you substitute nu value equal to 0, you will be getting 0 value. So your curve was, I will draw the curve again here. The experimental analysis of data, they have plotted a curve which was something like this. here in the y-axis you had energy density and in the x-axis you had frequency. So this was your curve. So at the value of frequency equal to 0, the energy density value was 0. So which is correct according to the curve and according to the expression, it is matching. But when you consider the second case, which is for higher frequency, so that means higher frequency means nu is tending to infinite, that is high value of frequency. So when you apply it over here in your energy density, so when you put infinite value instead of nu, you will be getting the entire value will become infinite. So what? When your frequency is in infinite range, what is infinite range? Infinite range means ultraviolet range. So when your frequency is in the range of ultraviolet, your energy density becomes infinite. That means u nu, energy density, is unpredictable. You can't predict the value of energy density because it is becoming infinite. How do you calculate the value of infinite? You can't be able to predict the value. But according to this graph, at a lower frequency, that is nu equal to 0, your energy density was 0, which was correct. First case was correct. But when your frequency increases, this is your frequency increase. This, according to the curve, this is a maximum value of energy density. This is a maximum value, U max. And later, as the frequency is increasing, the curve is decreasing downward. But this is not matching with this case. So this case is what? This is wrong actually. So this condition actually is known as ultraviolet catastrophe. What is this condition? The condition where when the frequency becomes infinite, that is the frequency becomes the UV range, one of the frequency in the UV range, then the energy density becomes infinite. That means you can't predict the value of energy density. So since it was leading to ultraviolet catastrophe and since it was not matching with the experimental curve, Planck assumed some other case. What did Planck assume? So Planck assumed that, like for the average energy calculation, he did it in the discrete form. Instead of taking it as a continuous form of energy, he has taken it in the discrete form. So instead, if you remember, we calculate the average energy per degree of freedom to be equal to 0 to infinite e power minus e by kBt divided by 0 to infinity e power minus e by kBt. If you remember, this was a formula to find the average value of E, right? So instead of taking continuous form, so integration represent what? Integration represent continuous form. So if certain data is in continuous form, only then you can find the integration. If it is in discrete form, so if it is discrete form means you cannot use integration, then you will use summation. You will just add it. Instead of integration, you will do summation. So what Planck did is, instead of integrating this value, since earlier they took it as continuous, now they are taking it as discrete. So he found expectation value, that is average energy per degree of freedom, equal to summation nh nu e power minus nh nu by kT divided by summation e power minus nh nu by kT. So by calculating, he got E bar is equal to, which is expectation of E, is equal to h nu by e power h nu by kT minus 1. So this was the value of average value of energy per degree of freedom. Now just substitute this in the energy density equation. What was energy density equation? U nu was energy density, is equal to Jeans number. What is Jeans number? N nu, right? What is N nu? 8 pi nu square by C cube into average energy value. What is average energy value? This. Just substitute it here. So by substituting, you will get U nu is equal to 8 pi nu square by C cube into h nu by e power h nu by kt minus 1. So this expression which was given by Planck's, this is known as Planck's distribution formula. So what is that one thing he did it different was, he instead of taking it as continuous energy, he took it as discrete form of energy and he did with summation instead of integration and found out this result. Now we will see each case. What are the two cases we had? One for lower frequency and another for higher frequency, right? So let's check if it is giving correct answer now according to the curve. If it is matching or not, we will see. If it is coming like this, or it was earlier case it was going to infinite, whether it is going to infinite or it is matching with the experimental curve or not, we will see in few minutes. So this is the first. What was the first case? For short frequency. Short frequency means what? We can even call it as high wavelength, right? Why? Because we know C is equal to nu lambda. That means nu is equal to C by lambda. So if you see, nu and lambda are inversely proportional. Nu is inversely proportional to lambda. So when you are finding for lower value of frequency means it is indirectly you are finding for higher value of wavelength, since it is inversely proportional. So for short frequency means high value of lambda. So just apply it here. So your this will be limit in U nu, you will be applying short frequency. What is short frequency? That means nu is tending to 0. So since nu is very low, so we can say h nu is very much lesser than kt. Since nu is approaching to 0, that means h nu value is lesser than kt. Just assume, just remember this one. Okay. So this was your expression, 8 pi nu square by C cube into h nu by, you have this expression, right? Now if you remember, this is one formula, e power x series, exponential series. If you open this, you will be getting 1 plus x square by 2 plus so on. Here the argument is x, but if you see here, the argument is h nu by kt. So instead of x, wherever x is there, just take it as h nu by kt. So by opening e power h nu by kt, you will be getting 1 plus the argument is h nu by kt and so on. And you have already, after this series you have minus 1, so put that minus 1 also. Now you are not writing higher order terms, which is h nu by kt square and so on, you are not writing because h nu is already very much lesser than kt. So when you take higher powers, it will be negligible. So you are avoiding that series. So you are left with only this term. Just cancel 1 and 1. This h nu and h nu. This kt will go to the numerator and thereby you will be getting 8 pi nu square by C cube into kt. This expression. Now if you remember, this was the earlier cases. Before the Planck, what expression did we have? We had U nu equal to Jeans number 8 pi nu square by C cube into energy density, we got it as, into average energy per degree of freedom, we got it as kt, right? This is matching with this case. If you remember for the first case, that is lower frequency, our graphical value as well as the experimental value was matching, that was correct. Only discrepancy was in higher value of frequency. So this is matching with the earlier one. Now let us see for long wavelength. So when you are putting, according to the graph, when you are putting 0 value, this becomes 0 and which is correct for frequency. This is frequency and this is energy density. When frequency is 0, energy density is also 0. So this is again correct only. Let's see for longer wavelength. Now case 2, which is for higher wavelength. Higher frequency. So case 2 is high frequency. High frequency means what? Low wavelength, because they are inversely proportional to each other, right? So this is actually Vane's law. This is also known as Vane's law. The earlier one, that is low frequency, was known as Rayleigh-Jean's law, and high frequency law is known as Vane's law. This you have to remember. So high frequency means you are taking frequency value tending to infinite. So you can gradually write h nu value is greater than kT. Why? Because now your nu value is greater, that is nu is tending to infinite. So h nu value will be greater than kT. In the previous case, since nu was tending to 0, so you took h nu lesser than kT. Now this is tending to infinity, so you can write it as h nu is greater than kT. So just apply the limit here, limit u nu, and nu is tending to infinite now. So when you apply it over here, 8 pi nu square by c cube into h nu by, now since h nu is very much greater than kT, that means h nu by kT is very much greater than 1. That means e power same value h nu by kT will also be greater than 1. So if you see here, this value is greater than 1. So we can neglect the 1 from here, because this entire value is greater than, very much greater than 1. See here. So just neglect the 1 here. So you will be getting e power h nu by kT, which is 8 pi h nu cube by c cube. Just take it to the numerator. You will be getting minus e power minus h nu by kT. So this is the energy density value for high value of frequency. So just apply it over here. So when you apply it, when you put the value of frequency to be infinite, you will not be getting infinite value. Instead you will be getting some finite value. So just if you take the curve, it will be matching with the experimental as well as the graphical curve. Now if you want to find the maximum energy density, that is the value of frequency at which the energy density is maximum. So just differentiate this u nu. So you want to find u nu max. You are going to find u nu max, right? You want to get the value of u nu max. So you need to know the value of frequency at which the energy density is becoming maximum. How do you find that? Just take the differential with respect to nu. That is, at what value you want to find? That is, you want to find the frequency value, right, at maximum energy density. So just differentiate with respect to nu and equate it to 0. So while differentiating this two equation, you will be getting nu is equal to 3. You will be getting nu is equal to 3 kT by h. This was with respect to frequency you did, right? You got, while calculating for frequency, you got frequency is equal to 3 kT by h, right? So this entire calculation you did it for frequency. That is first case low frequency, then second case high frequency, everything you did. Now the same thing if you do it for wavelength, you will also be getting two result. So how do you do for wavelength? So we know c is equal to nu lambda, and from here if you find nu is equal to c by lambda, and if you differentiate d nu, you will be getting minus c by lambda square d lambda. You got it this. So just substitute in the two equation whatever we have derived, nu there and d nu, you will be getting in terms of lambda, and in the similar way you will be getting two equation, and that will be exactly matching the graphical curve, and thereby you will be getting value of energy density. So in the same way, if you want to find the maximum, that is the value of lambda at which u lambda is maximum, that is energy density is maximum at which value of lambda. So in order to find that, just differentiate u lambda with d lambda and equate it with 0. So you will be getting lambda is equal to hc by 3 kt. This two thing you have to remember. So from this expression, what do we find? Frequency is directly proportional to temperature. This is a very important result. From here, what do we find? Lambda is inversely proportional to temperature. Lambda is inversely proportional to temperature. Another result which is very much important. So from based on these two things, you can get it in numerical as well. For example, let's say this is your curve, this is your frequency, this is one curve, 2, 3. So this is nu 1, this is nu 2, this is nu 3, and this particular curve has temperature T1, this particular curve has temperature T2, this particular curve has temperature T3. So from the graph it is evident that nu 3 is greater than nu 2 is greater than nu 1, but we also know nu is directly proportional to temperature. Just now we saw, since nu was equal to 3 kt by h, so nu is proportional to T. So we can say the corresponding temperature of nu 3 is T3. So T3 is greater than T2 is greater than T1. So this is the numerical problem with respect to this expression. Similarly, we can say, we can do for lambda also. Lambda is inversely proportional to temperature. When lambda increases, temperature value decreases. So that again you have one more problem. So with this lecture gets completed. So if you have any kind of doubt from the lecture that I have just taught, just comment down. I'll answer the queries. And if you liked my video, just like it and share it with your friends and comment it. So let's again see in the next video. Till then, bye.